Hey everybody, welcome to Functions with me. Previously, we have been discussing relations. Functions are just a very specific type of relation, and it's got like some extra qualifications on it. Best part of it is though, we're already pretty familiar with functions. We've definitely seen these before, so hopefully this actually feels like a little bit of review today. Types of functions you may have encountered before. We've got continuous and differentiable functions from calculus. You may not have thought of it this way before, but a computer program is also a function. And then for all my business people out there, we've got supply and demand. So then what do all these have in common? All of these have inputs that gets put into our function. And then the function is going to spit out some output. If I were to tell you that the input was 2, would give you an output of 4, you might think, oh, maybe the function is 2x. And if I give you some more information, I'm like, oh, but the input is 3, you're going to get an output of 9. You're like, well, maybe it's x squared. Probably is, unless we've got like some funky piecewise thing going on. But the important part is I only got out one output every time I had an input. And that's the extra qualification that we're going to stick onto relations now. So let's formally define function. So a function or a mapping from set A to B is just a relation from A to B, such that, and then here we go, scary quantifiers. For all the A's, there exists a unique B such that A is in B. Let's unpack that really quick. So for all the A's, use the whole domain. That's what that first quantifier says. And then there exists a unique B, so that's a fancy way of saying only one output. And that's one word. Such that the ordered pair AB is going to be in the relation F. But that's a function now because we've got those extra qualifications on there. So we can denote this function saying f is going from A to B, and we also say f of A equals B, which we should be very familiar with, and that is the notation that we're going to use. Also, a couple more vocabulary words to throw at you. We say that A is the domain of F and B is the codomain of F. Let's do a picture of what this definition would look like real quick. First one, if we have like a graph, we'll say here are axes, and then if we have a picture that looks like this, that means right here for like 1, we're going to have more than one output. Okay. This would be not a function. Something that would be a function, oops. So this is x squared equals y, just in case you're wondering. So something that would be a function is our beloved y equals x squared. So this is a function because every input has exactly, see, like if we come through here and we draw a bunch of lines, it only passes through the graph once. So every input is going to only have one output, unlike before. Okay, that's one sort of picture to think about. Another one to think about is maybe if we have this set of 1, 2, 3, and 4, and it's getting mapped to, we'll say this is A and this is B. It's getting mapped to 5, 6, and 7. So if we have like 1 goes to 5, and we'll say that 2 goes to 5, 3 goes to 6, 3 goes to 7, or 4 goes to 7. This is okay. We have 2 things going to 5, but something that would make it not okay is saying 2 goes to 5 and 2 goes to 6. So now 2 is going multiple places. So again, not a function. And then let's do another example. We're going to use the same A and B. 1, 2, 3, 4, 5, 6, 7. We're going to keep it simple. Nobody's going to go double places. Now, if we say that this is our function, I'm going to say, nope, this is not a function. Here we go. For this qualifier right here, for all A in A. That means we have to use everything in the domain. 4 did not get used. So this is also not a function. And then let's just do one where we do get to have a function. Scoot up here. So let's use the same sets again. So a function could be 1 to 5, 2 to 6, 3 to 7, and then also 4 to 7. This would be a function. We have used everything in the domain, and nobody goes 2 different places. All right, let's look at another example. Let's look at these relations. Let's try and figure out which of these relations are going to be functions. So we've got our set A, which is going to be 1, 2, 3. We have our set B, 2, 4, 6, 8. The first relation on our list is actually a relation that I used before. But notice right off the bat, we have 1 goes to 2 and we have 1 goes to 6. So this is not a function. And then the next relation, we have 1 goes to 2, we have 2 goes to 4, we have 3 goes to 6. We did not use everything in B. That is okay. We used everything in A, and that's what we really, really need to look for. And 1, 2, and 3 only get mapped one place each. So this is a function. And then T, we have 1 goes to 8, we have 3 goes to 6. We have not used B again, or not used all of B again. That's okay. This falls apart because what about 2? So 2 is in A, which means it needs to get mapped somewhere. So this one is also not a function. Then just to make sure that we're super all on the same page, I'm going to do one more example, figuring out function or not. If I were to say we have a function going from the reals to the reals, and it is defined by f of x equals the square root of x, is this a function? Think about it. Does it go 2 places? It doesn't go 2 places. That's not the problem. If I had said like plus or minus, then that would be the problem. Now it's going 2 places. But we just have this positive square root, so that's not a problem. Then we've got maybe negative problem. I'm like, well, technically that would be like imaginary numbers. Be like, okay, but this would need to be f would need to map into the complex numbers. I've said it can't map into the complex numbers. I only want outputs that are real, which means I can't have negative inputs. So only want real outputs. So that means no negative inputs. So then not a function. So let's restrict the domain a little bit. Let's go with, okay, fine. Positive and 0 going to the reals, square root. Yes. Now we've fixed it. This one is a function. Incidentally, just as a comment, we could have also fixed our problem, so to speak. So if we had kept it R, but then opened up the codomain to include complex numbers, then we would have been allowed to plug in negative numbers, and we would still have a place for it to go. Okay. So I think at this point, we definitely understand what a function is. But notice that in some of these examples, a lot of these examples actually, we did not map to the whole codomain. So like for instance, this one, we did not map to all of R. We only mapped to the positive part of R and 0. So of course, we have a name for that. The range is where everything gets mapped to. So the range of f for every is all the b's in the codomain such that we have an a that gets mapped to it. More concisely, it's all the b's that get mapped to. So let's go ahead, let's find some domains, some ranges, and codomains for the following functions. So we've got the domain here is going to be R0 plus. It's really easy to pick out. Then the range, let's do it this way. Range is going to be everything that it hits, which is going to be positive reals and include 0. By the way, that's what that little 0 down on the bottom is like. Yeah, this is the reals and also 0. And then the codomain is going to be all of R. You can just pick the codomain off of right there. Okay, let's go ahead. Let's do it again. So for this one, we've got the domain is all of R. And then we've got the codomain, easy to pick out, also all of R. But the range, not necessarily going to be all of R. So let's think about this guy. We know that squares are always 0 or positive, but now we have a negative sitting on top of it. So that means it's going to be negative numbers and possibly 0. Then last one, I didn't tell you what sets this was going in between, but that's actually not going to stop us from figuring out most of these answers. So we've got 1, 2, and 3 is what is sitting in the first position. That's our input. Got 1, 2, and 3. And then our range is the output. So 4, 5, 6. And then codomain, we weren't told, again, what the sets were. And so how do we know the codomain? Anything that includes the range is good enough. So we can just say, it's just the same thing. There's a codomain that works. Is that the only codomain that works? No, because you could have lots of things in there that we didn't even use. So another example of a codomain that would work would be 4, 5, 6, 7, 8 maybe. Don't even have to stop there. We could say that the codomain was all of the integers, or even all of the real numbers. All of those codomains work. Okay. I know we already talked about composition of relations, but we're going to do it again for composition of functions, just to make sure that we're all super on the same page. So composition of functions, we've got a function going from A to B, and we have a function going from P to C, and we can link these two functions together using composition. The important part is the codomain of F is equal to the domain of G. So here's our formal definition of composition of functions. If we've got function F, function G, then G composed with F is going to start at A and end at C. And it's just you stick F inside of the G function. Let's do a little bit of an example of what this would look like as a picture. Let's say we've got F is going from here to here. Oops. There we go. Let's say this is our function F. I did not map to 9. That is okay. Functions don't have to hit everything in the codomain. And then we're going to do function G. We're going to say that goes to circle. 6 also goes to circle. 7 is going to go to heart. 8 goes to square. 9 goes to square. And this is going to be G. So G has to use everything in its domain. It has to use 9. And then, I don't know, I looked at this and this made me uncomfortable and I was like, oh, that seems like a problem, guys. It's not a problem. Why? Because in order to be a function, you need everything in your domain to get mapped to something. One thing specifically. And that's what G composed with F does. New color. Okay. So what happens is we have 1 is going to get mapped to circle. We have 2. Let's see, it goes to 7. And then that goes to heart. We have 3, which is also going to get mapped to circle. And then we have 4, which gets mapped to square. So everything got mapped somewhere. Everything in A got mapped somewhere. Our function G composed of F starts at A and ends in C. Yes, we kind of skipped over this 9. That's not a problem. Everything got mapped to exactly one place over here in C. So we haven't broken any rules. We just need the codomain to equal the domain. We don't need the range of F to match up with the domain of G. It's okay to have extra things. Okay, I think I have beat that horse to death now. Let's look at maybe some more traditional examples of functions we're used to looking at. We've got F is going to go from R to R, and G is also going to go from R to R. And I have 2 different functions to look at. We have x squared for F, and we have 2x plus 3 for 3. Let's go ahead and find the following compositions. I personally, first thing I do is I always write it like that. It's easy to remember because G and F stay in the same order, and it's just much easier for my brain to think about. Just like, okay, so what was f of x? That was x squared. So everywhere in G that I have an x, I'm just going to stick an x squared. Okay. So then just taking this back to my point about range and domain and stuff, the range of F would just be the positives and 0, because that's what squares do. That was not equal to the whole reals, which is the domain of G. And that is okay. Let's see one more example. F composed with G. So this time we're going to stick G inside of F. So we said G was 2x plus 3. So now we go to F and we stick the G function in everywhere we have an x. So hopefully you can see that this and this are two very different functions. So order most certainly matters. All right, one more topic. Now that we have composition of functions, we're going to talk about a very, very special function, the identity function. So the identity function, much like the identity relation, we already talked about it. It would be defined on a set A, and it just maps every element to itself. How is this related to composition of functions? There's this theorem that I'm very surprised that the book did not mention, but it's a cool theorem. So we're going to talk about it briefly. If F is getting mapped from A to B, then the identity function on B composed with F is just going to give us F back. And then if we compose the identity function of A with F, so F of the identity function on A, we're going to get F back. Since F is going from A to B, that means you have to do different identity functions. So F goes from A to B. The identity function of B would just be going from B to B. And so then if we were to do IB composed with F, that means you would want to start at A and go to B, and then the codomain and domain of the identity function match up. Oops. So then we would have A goes to B is kind of what it would look like. Meanwhile, if we do it the other way, if we have the identity function on A, that goes A to A. And so when we switch this around, we have to be able to plug in A stuff to F. So you would have the identity function on A going from A to A, and then F going to B. So like this would be the identity function, that would be F. So yeah, it kind of depends on, if A and B are the same set, then you would have the same identity function, but you might not have that they're the same set. Anyway, let's go ahead and prove this really quick. It's not elaborate at all. The first one we have is the identity function composed with F. So then let's make this a little bit more formal. Let's say let X be in A. Then when we do the composition of functions, we have I of f of x is going to be equal to just f of x, because f of x would have been an element in B. So let's go up and add that to the beginning. So then f of x is an element of B, which means that our identity function on B is just going to be f of x. So that's one of them. The other one, we're going to do it again. We're going to say let x be an element of A. Then if we do f composed with IA, now we're going to stick the identity function into F, but the identity function of x is just going to be x So once again, you get back to F. So again, it's really just applying the definition of composition. It's not really that exciting. However, we will prove things that are more exciting next time. So stay tuned.